Okay, good. All right. So this is, I think, fourth video of Calc 3 stuff. So right now I'm getting to the point where I'm going deeper into the concepts of the calculus of, I guess, vectors. So chapter 12.2 today from Professor Leonard's. This is derivatives and integrals of basic vector functions. So we're going into, I think, partial derivatives. I'll start getting into that week, but from what I've seen, you're not you're just only taking one of those variables. Let's say you have I don't know, the integral of x squared dy. You're taking the integral with respect to y, but the x doesn't change. I could be wrong. That's from what I've seen so far. Although, yeah, I think I'll get to that in next 2-3 days, and hopefully get just touch a bit of double, triple integrals. But I know that might be a little bit down the road. But from what I see, I'll be doing all right. But anyway, for derivatives of vector functions, so it's quite similar from the proofs and whatnot, but essentially with 2Ds or with Calc 1 and Calc 2, it was approximating a change in the curve. So because derivatives are just essentially limits, so you can just go smaller of the change until it becomes so insignificant. Notice, oh, it's similar to like a rise over run, but on a curve instead. It's not linear. But for vectors, however, vectors, remember that they're just, think of it as an arrow that has a specific length and points at a specific direction, and that can also be a curve most likely. But if we're just talking about the vector specifically, the change of that vector, in a sense, what it does is it will be tangent to a space curve. So what I mean by that is this. So let's say you have a curve. Let's say you just have a curve in 2D. And let's pick this point. You can have a vector. You will be able to make a vector that starts from the origin to where you decided to put that point on the curve, and that would essentially be that change. And let's say you wanted to move it a little bit up, then that would be your delta x, which the delta x is the change. And the way I would show it is just showing you guys here. So right here, it's a little bit hard to see, but essentially those are the changes. This is the proof right here of the delta x, and that's essentially what it does. It approximates a change in how long this vector will be from the origin to wherever you decided to go, but also what direction, because that point may be here, but now the point can be up there. So if you want to approximate that change too. So and same thing, just like tangent to a line or to a curve, now you do it to a space curve. So now you have to consider that not only you have a specific direction that sometimes the curve can go, but now with the vector, now you have to add the consideration of a length of vector, because let's say the curve's all the way out here from the origin, or maybe the curve is just right next to the origin. So that also changes, even if it's the exact same direction, the length, how long this vector can be changes. So graph that I showed you, it's essentially like if you had two secant vectors or a secant vector, but that secant vector, if you had this point gets so small to the point where it just becomes a tangent vector, where it's just looking exactly like the graph. So that's the way I would explain it. Yeah, this is just proofs that explains that that if you took the derivatives of your I, j, and k's, which are the coordinate, you think of them as like coordinate systems in whenever you plot your xyz points on a graph, that would give you the derivative of your vector. So in other words, how you look regular functions with derivatives, you can do the exact same thing with vectors. You can write them out in the brackets, or you can put them in ijk. So it's the exact same thing. But when you take the derivative of a vector, you find the tangent vector to whatever point you have specifically found. But let's say you're doing it for a general case, you can also do it for the general case too, which is you can find the tangent vector that applies to the entire original vector for whatever point you choose. And if you can also find the unit tangent vector to that derivative as well, but that's in the next chapter. But everything it all works there. So essentially, when you take the derivative, we are finding the direct, how when you take a derivative, you will eventually get a tangent line, or when you get you will get a tangent line to whatever the curve is. And but because we have vectors, that's why it's a direction vector. You're saying, all right, well, if okay, so is this up? Okay, so I cut out. Oh yeah, so I was mentioning how with the vector functions and you take that derivative. Well, you just when you do that, I think I mentioned that we found the direction vector. So let's say this is I'm gonna use pencils because that's what I have. So let's say this is the original vector function, and let's say it's going this way. What we essentially were saying is we found the direction vector to that tangent point we want. Because let's say I look for the point, let's say here. I already found the direction of this tangent line, and it will always be like that because that's the vector. It's a space curve vector, and the space curve. What I mean is because we are in 3D, so we have to consider the fact that not only do we need to have a direction of this, but it can also have a length of whatever it is. And that can also be done in 2D. But we also have to consider now our third coordinates in a sense, because now you can literally bend to whatever you want. Sometimes maybe and the reason why is because sometimes typically you would only have 4 quadrants in 2D where okay, your x both negative, but now you have 3 things to consider. Which ones are positive, which ones are negative for your XYZ coordinates. So yeah. And that is for and when we're working in derivatives for when you're looking derivatives for these functions, you don't use x's or y's or z's, you use the variable t. And t, some people like to think of it as if it's equated to time. Sure, that can work as long as you have your ij's in case. For me personally, I like to think of it as it's t, t for time, and you'd say the vector r, or the vector is named r, and for t, which means at x amount of seconds, where are we at on the graph? And considering that these are position vectors too, we always start at 0, 0, 0. But then, as let's say time has passed 2 seconds, where are we at? Or what about 4? All right, how much change was that in terms of how would I say how much of the direction has changed? So the vectors here, that where are we pointing now at, or how far off are we now? So that's what I would say. And yeah, it's the direction of the tangent line to the original curve. Yeah, it's the direction of the tangent line to the original curve at any time with t. So I guess one more way to put it is, let's say you had a vector in 2D and you found that tangent line. When we do it for a vector, you're essentially saying, okay, where's the tangent line that we found, where's it pointing at? What direction is it going? That's literally all the difference when taking derivatives of vectors. Because because normally a regular tangent line, you already have length. But now you need a direction because it's a vector. So prerequisite for vectors, you need length and direction. This is, what did I write here? The following examples will show what the derivative and tangent line is doing and relate them to the original vector function. Oh, okay. Oh, okay, so this stuff is just essentially point of tangency, and I guess the way I would explain the point of tangency would be that specific location that you're looking for. that you would want to find that direction of that vector that tells you, oh, okay, that when we find the tangent line or when we take the derivative, we find the tangent line, but now we know, hey, our tangent line is pointing in this direction across all three x, y, z. But if we want to go more specific in there, these are just examples. So it says sketch. It's just basically how to find the thing, and then you find your tangent vector at the point of tangency. Tangent vector. Forget it. Okay. Hang on. Bit tired. My tangent vector. This is so okay. 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 No, this is just subbing stuff in. Okay. Oh yeah, and okay. Before I go to point of tangency, I'm gonna just talk. So the unit tangent vector, what it does is when you take the derivative of the original curve, you can also find what that of that tangent vector. What would happen? You had to squeeze it to a length of 1. If you've seen regular descriptions or visualizations of the tangent line, it seems like it goes for infinity. What would happen if you wanted to treat it like a vector and shrink it to 1? That's how that would work. That's how it would work with. And what you essentially do is you take that derivative and then you find its length or magnitude, which you would have to square everything and then put it in the square root. But that would be probably for right now is not the time to to do the entire procedure. I would have to go back to the first video because those are just the basics. But I'm just explaining it. I can really distill myself and know that what I'm talking about. Okay, it's fine. Okay, got a vector tangent curve. Yeah. Okay, what is this? This is POT. Point of tendency, in a sense, they will, to find the point of tendency, they will already give you what t value you're looking for, in a sense. At that time is where essentially the basically they're just kind of giving you the point of, I want you to find me what the value is at this point. But then you have to take the general case and then reapply it to your specific case. So that's how I would put it. Although if I do find something else that more appealing than that definition, at least from when I looked at it and said, all right, this is how I would define it, I'll come back and maybe just put it in the description, most likely. This is the direction of the tangent. Okay, yeah. And yeah, when we do the unit vectors and whatnot, they will give us direction, but the length is always shrunk to 1. And yeah, the point of tangency in the sense where it connects, it's the point where it touches the graph and you're saying, okay, I want to see what happens. What is the value of this direction? Where's it located on the curve? And what direction will it have when I take the derivative, I find out what it is? How does that look like? So the point of tangency, there's nothing special about it. It's just I wanna find what happens. when the tangent line is here, and then what's the direction of that thing. So yeah. So I'll end it there with the point tangent. It's I already give you the point. It's like what does that tangent line look like? Where's it pointing at? How long? If we want to find the length of it at 1, which is the unit tangent vector, yeah, how would that look like? So that's nothing special about that. Okay, so for tangent line, see how you need a point tangent vector. Okay, so okay, nothing out of the ordinary. Okay, these are all just examples. Okay, and then integrals, they're basically like your regular calc 1, calc 2 antiderivatives. Now you just need to remind yourself to put it back in a vector form. So that's as much as I would say, because when you're doing this, when you get to the, let's say it's a definite integral. If it's a definite integral, which most likely it will be, you will not subtract values. You, as in like 1/2 plus 1/3 plus 1/4 minus whatever it is. That's not how it works. The way it works is your ijk still act like your xyz vector. So you will only subtract things that are for your x's, your y's, and your z's. You don't add or subtract them between each other. Leave them intact. So for this problem that I have, or that I have in front of me, I accidentally did this, where I thought it was 13/12, but that's the actual answer, because you leave it in a vector form. So right here, so the integral was taken from 1 and 0. So this is 1/2 times 1 squared. Here's 1/2 times 0, 1/2 times 0 squared. These are for my x value. So I only subtract them between these two. This is my y, this is my y. So you subtract them between each other. This is your z, You subtract them between each other to get that. But at the end, all I got is just have 1/3, 1/4, because the left side, which I substituted in 1, it's 1/2 times 1 squared plus 1/3 times 1 cubed plus 1/4 times 1 cortex, so 4. Fuck. All right. All right. And the right side was 1/2 0 squared plus 1/3 0 cubed plus 1/4 0 cortex times 0 to the quarter power, which all of that equals 0. So take it by z, nothing happens. And yeah, even with integration, you can get as far as integration by parts. You can do u sub. You probably have like your inverse sine tangents, ln. So trig sub maybe too. Anything's possible, to be honest. Okay, these are also more examples, and yeah, you can also go backwards too. So let's say you have your antiderivative, but then you say at, let's say, the point of not point of tendency, but let's say if you have the derivative, you need to get back to the original function. Or in other words, you have the tangent. Let's say you have the tangent vector. You have the coordinates for the tangent vector. Cool. But using that, you need to go back to find out, okay, what is my original vector? I'm going to take the antiderivative. But then it'll tell you something as in, if the vector at 0, when the value is 0, let's say I plus k, there's no j. So in other words, it's saying when the vector has a value of 0, then, or when 0 seconds have passed, because it's r of t, the vectors are, but at t, 0 seconds have passed, you are at your coordinates on the graph are 1, 0, 1, which means your x is 1, your y is 0, and your z is 1. They're all positive. So then there, essentially, your plus c would exist. But your plus c, if you were to take the antiderivative of everything, you would have 3 c's, 1 for I, 1 for j, 1 for k, but 3 constants make up 1 constant, correct? Because you can just add them up together and you still get a constant. So you don't have to write all 3 c's. You can just say a big fat plus c, because the big fat plus c is 3 constants. smash into one, and it doesn't matter anyway because you'll need the constants anyway. So might as well just have them all into one. So, and the reason that's important, the constant, because they will tell you if you have any missing variables when you integrate everything and when you add, subtract, integrate everything, you will find out that, hey, maybe your answer isn't all correct, or there are things missing. That C tells you, oh, here are the missing parts, by the way. So yeah. Let's see. I didn't show you this problem. So yeah. So this is the original function, and it's at r equals 0. You have I plus k 1, 0, 1. When you do all the integration, I end up here. So I'm at r is worth r when the time has passed 0. I have 2 times 0 I, so that's 0. 2 times 0 j, that's 0. 2 times 0 k, that's 0, plus my big fat c, which are 3 constants. But I said that this has to equal I plus k, but right now we have 0 plus 0 plus 0 minus 0 plus c, because of the zeros, because of the minus right here. And then I'm left with c. Yeah. Then I'm left with c right here. Cool. So, oh yeah, by the way, if you're wondering where the minus came from, right here. So that's part of the original problem. So I'm left basically with 0 plus c equal to I plus k. Well, if that's the case, then c is I plus k. So when we take back the original integration, or when we integrate to get the original answer, we're basically saying this, that when at r equals 0, our c is equal to I plus k, so we would have to rewrite in this format, so that whenever we had to substitute 0 into our original function, we would just get the I plus k that we needed to get our coordinates points on the systems. So that's basically how the integration with vectors, that's why it's important, because that constant, even though it's part of there, it's essentially a constant vector that can push things up in a sense. It's like with the I like to think of it as the sine and cosine, where you have, maybe, let's say, when we begin to start graphing things out, we have, let's say, 3 sine x plus 1. That plus 1 at the end, that shifts everything 1 up. So think of it as that constant vector, where that thing can actually move your graph a little bit anywhere. Because that extra I plus k, typically you would start at 0 if you didn't have your x value I. But because we have that constant equal to I plus k, we're saying, oh, now you move 1. So that's one way to think about it. But I wouldn't use it literally to explain those types of things. Those have more appropriate terminology. But for those who need a little bit of an example of where did I use this before, because all things stack up. So yeah. All right. Okay, this is just another example. Okay, 12. Yeah, chapter 12.3, section 12.3. My bad. Arc length and arc length parameterization. Okay, so this was the part where I mentioned about I mentioned how you can find a unit tangent vector just by using the derivative. So what you would do there. Okay, so wait, what am I looking at? Okay, this is just okay, these are just the proofs right now. So it's giving you actual arc length. Okay, so arc length. Okay. So so arc length is just kind of telling you, all right, how long is this how long is the, not how long, but the length of derivative. Okay. Okay, I need to explain that thing first. I was about to go into parameterization. Okay, but arc length, it basically says it's how long the original curve is when you give t, or time, a specific distance to go to. That's what arc length is. So let's say you gave me x formula, and let's say I wanted to find out how long the curve, it could be like a vector, or like a regular curve, a vector, whatever it is. And you said, I want you to go from when time is equal to 0 to time is equal to, I don't know, 2 pi. Okay, Cool. So, but to find that, essentially, we need to take I guess, with the time that I have, knowing of how long this recording can go, steps just basically find that tangent curve. So, so you need to take a derivative and then find the magnitude. Magnitude is the length, and you're trying to find arc length. So that's why you take the. That's why once you take the derivative, you need to find the length for the magnitude. So it's those weird brackets. Okay, so I'm going to show any proof quickly. FTHD. Okay. Okay. Well, this comes from parametric equations. So not old examples, but just to get people to understand why I don't really go over these things, but that might help. Okay, so yeah, so arc length in a sense is just basically, if I gave you this from this time point to this time point, how long is the curve along that time frame? And to do that, you would need to you need to go from you need to take the derivative, find that magnitude, but then you would have to integrate over that time frame, because when you're looking for something that goes from this point to this point, that's essentially area, not area, but it is a curve. So you need to find out how long that is anyway. So kind of let's say a fun process. So, okay, these are just how many tests. God damn, how many did I make? Hold on, let me see how many examples I actually made this. Okay, good. All right. Reparameterization. That's a very long word. Anyway, changing basically reparameterization is deciding where we change to integrate in a sense. If I remember correctly, I know we did one. Oh, it's reparameterization is similar to how we re-index series. So when let's say we had a series that started at subtract 3 from the series or from the big sigma sign, but you have to add 3 from the other side to make sure basically everything has to be evenly balanced. But here, when we're doing it for vector functions for these types of things, where not only you have to consider what type changes and then your position, but you also have that z-axis, which means now your entire position of space-time, now you have to consider that too. So, and however, this only works for smooth curves, at least with the limited knowledge that I know, we can only go up to smooth curves. Smooth curves mean that you have no cusps, so any pointy things there, because when you try and find a derivative of something that's pointy, that's infinite. That's infinite because there's not necessarily anything for you to graph on. You're just at an infinite point that just is like this forever. And then no infinite slope, so you may have seen something that goes like this forever and then it comes back. That's an infinite slope. It's almost as if it behaves similar to, not behaves, but you just can't tell that like how much is depending. And no gaps, so no holes, no nothing, and no asymptotes either, because how are you gonna find a derivative of an asymptote? And it has to be on the original. Those things cannot exist on an original curve. So not the derivative, but the original function. And why would someone want to reparameterize? So that they can find the unit tangent vector, which means that line that we have found when we took our derivative on a specific point on this vector, we want to say, hey, I want to shrink it to 1. That's essentially why. That's why people reparameterize. It's the same thing how we did it with series when we re-indexed and said, oh, I wanted to start here. Why? Because it's a lot easier. It's a lot easier. Plus, you get specific values, you may be able to find a pattern. Because when you start way at the beginning, you can notice the pattern quickly accelerating. Taylor series, you can't really do that. I mean, you can take some values out when you're trying to find the solution, because sometimes they may not fit in into when you're trying to explain the pattern and collectively put it into something of eloquence. So, yep. Let's see if I can find a quick example because I know I'm running out of time for the recording. I think I got like 8 minutes left before it kicks me out. Oh, yeah, essentially, you're trying to find a unit tangent vector. What is this arc length? With reparameterization, sure, you can also solve for time. So you can find out, okay, what time value is this? But then you have to ask yourself, then, okay, what is the S? And that S is the variable that we use as a kind of way of saying, it's like a position in a sense. Think of it as the S of t is when we had the displacement, velocity, and acceleration. That's just the first thing that comes up to me. Is like I think of, oh, what's going to be the change of this? But as time passes, so okay, it's not. This is okay. What is this? Oh, okay. These are just other stuff. Okay. Yeah, I wrote it here. Yeah, reparameterization, so we can find the vector function that will give us a unit tangent vector. I think I have time to show you guys. Yeah, probably. Yeah, okay, yeah, sure. I have one quick example. So the function is e of t times cosine ti plus e of t sine tj plus e of tk. And t time starts at 0, but can go up to wherever it wants. That's the thing. It's like, okay, well, but if we're going from 0 to infinity, how's that going to look like? So essentially you have to take the derivative and then find the magnitude of that. And when you do all of that, that's square root of 3 e to the power t. So yes, there's a lot of there's a product rule, and then you have to factor everything out and see what you can pull out in a sense. And then when you find all of that, you just essentially found that unit vector. And then you take that integral. You take the integral of that thing. Why? Because that is your formula of the arc length. Because remember, you're going from 0 to who knows where. So you need to find what that length is in a sense. But we have essentially now you can also find a formula that is based on t. So you can actually find out what t actually is. Like, where do we go from? Because right now it just says t0 to what? Okay. And that's essentially what we do is we say that yep. So, and when we do that, we give it a variable and we say s, which is the displacement or the place that we want to start. So then t is equal to ln s over square root of 3 plus 1. But in other words, s is square root of 3 times e to t minus 1. I'm just telling you what the answer is. And that's what that reparameterization is. It tells you, okay, now you found what t is. So that's as far as you're going to go. And yeah, when t is equal to 0, that's essentially what it's saying, is that ln s of square root of 3 plus 1 equals t. If you put it to 0, you're saying, okay, then what value of s do I put in there so I get 0? So that's that's the generalization of the formula. And it doesn't always have to be for anything that doesn't have specific endpoints. Because here's one that I have where find the value on where t is between 0 and 1, both ends included. And yeah, you take a derivative, you find that You find the length for the unit tangent vector. And then you have to integrate all that, which looks like a very big mess from the way I wrote it here. But yeah, the value L, or the L is essentially, which is the variable I gave you. L is where it tells you, hey, that's how you're going to define it in a sense. So yeah. Do we do it? It's only when we want to. It's only, as I mentioned, parameterization is done so that we can find that vector function that gives the unit tangent vector. Is it necessary? Hell yeah, because we use that a lot in vector calculus, but yeah, vector calculus if you like to call it. But yeah, so that's a little bit about it. Not often, if we're being honest. I think it's just really comes down to. I know it's more for the training vehicle, but then although I would ask myself, okay, but in the real world, where am I going to use this? So I'm probably gonna do a 2-minute rabbit hole after this recording. Okay, TNB frames. This okay. I'll have to do TNB frames right now time because I only have a proof right now, not any examples to show you. So I'll stop it here. But yeah, all right. All right, guys. Happy holidays, whatever you celebrate. I'll catch you another